In this video, we're going to go over a few different reactions in order to compare the Sn1 and the Sn2 mechanisms. So the first reaction we have up here is going to be a chloropropane, and it's going to be reacted with a sodium cyanide in a solution of acetone. Now notice, I've just got acetone written up here, but we don't know the chemical properties of acetone. So we need to look those up. So whenever you encounter a solvent that you're unfamiliar with, you should look it up online. There are many, many different solvents, and what you're really going to be looking for here is this going to be a protic solvent or an aprotic solvent? Now in this case, it may not matter that much, but if we look acetone up, we see that it is a basic ketone. Looks like that. That will be an aprotic solvent. So it's not going to participate in hydrogen binding. It's still going to be polar. That oxygen to carbon bond is very polar, but it's not going to have that hydrogen binding that could potentially interfere with the strength of our nucleophile. So we're not going to need to worry about the acetone itself. Glad we found that out. So the first thing we want to find out is this going to be an Sn1 or an Sn2? And to do that, we need to consider the big barriers to both of those reactions. The Sn1 has a big barrier of carbocation stability. The Sn2, the big barrier is going to be steric hindrance. For now, that's the only factor that we're going to look at in determining which of these reactions is going to happen. There are other factors that could be at play. We'll look at those later. For now, all we need to think about is how substituted is this carbon that's attached to that functional group. That's the carbon that we're looking at right there. We can see that it's only attached to one other carbon, so this is going to be a primary substitution, which means it's 1 degree. Well, when we looked at the Sn2, that is very favorable. That is going to proceed quite quickly. All right, so the Sn2 is favored. Check. What about the Sn1? Is the Sn2 going to be favored or disfavored? Now we want to keep that in mind, that what we're saying here is it favorable or not? Not, is it going to happen at all? Often, these reactions do compete with each other, even on a tiny little scale. It is possible that the Sn1 could still proceed, but it just proceeds so slowly that we're not even going to consider it. So, with the primary substitution, we're going to have horrible carbocation stability. So the Sn1 is disfavored. So we need to keep that in mind, that this is favorable versus disfavorable. As in, I might get some Sn1 products, but it might be like literally 1 in a billion molecules is an Sn1 product. So I don't even need to consider it. It's not going to be a high enough concentration to really worry about. So now that I've figured out which mechanism this is going to be, I need to draw out that mechanism. So to draw out the mechanism, I'm going to show that the cyanide here is going to be attacking that carbon. So I'm going to redraw this below to show my mechanism. So you should do this. Each time you encounter one of these reactions, when you're drawing it out, you should take the time to draw out the mechanism below. That will be part of your answer. That is, it's effectively the proof for your answer. So there's my substrate. I've drawn in my electron pairs that is going to be necessary because I'm going to need to show these electrons moving somewhere if they're going to move, or just not being involved if they're not. Then I've got sodium cyanide. The sodium will be a spectator. It's not going to do anything, so let's just draw it in black and leave it there. Then I've got my cyanide. Cyanide, let's put in blue, giving it a color to show that it's going to do something. So I've got cyanide. And cyanide, I've got a triple bond between the carbon and the nitrogen. If you're ever unsure of what these look like, you can always look them up. That's totally fine. So I've got carbons here, or electrons here, and overall it's a negative charge. So the carbon is going to be seeking that fourth bond, right? Carbons are going to be naturally stable with 4 bonds. So this carbon is going to be what attacks this carbon. We know that carbon has greater nucleophile strength than chlorine, just for our general trends. A carbon that has a negative charge associated is going to be a lot more basic. So these two electrons, this electron pair right here, this is going to be attacking this carbon. So I'm going to draw that arrow right there. And because that electron pair is attacking this carbon, this bond right here is going to be taken away by the chlorine. So effectively, this carbon is pushing this chlorine out. Now, our final step here, our final product, is going to be based on that reaction. So I'm going to get, so there's our final product. Notice, I didn't draw my intermediate step. That's something that we aren't going to need to do going forward, just because it is an intermediate step. This whole thing happens all at once. We don't want to get confused thinking there is a second step in the Sn2 mechanism. So when we look at these, we are just going to draw that single step and move on. So I can see that this is going to be my products. I'm going to have this carbon attached to a nitrogen. This is something that we have not named yet. We're not going to get into it. But that allows me to then draw my final product. So this, just going to draw it like that. Okay. Plus, and then I've got this chlorine left over. That's going to be paired with that sodium cation that was a spectator. So I've got NaCl left over. So that's my whole reaction. So if I were given this question on a test or in homework, all I would do is I would figure out which mechanisms this is going to work according to, draw that mechanism, and then give my final answer. There we go. So for the second reaction I'm looking at here, I have an alcohol on a tertiary substituted carbon, and it's being reacted with sodium bromide in a solution of H2O along with some sulfuric acid. Why is this sulfuric acid here? Is sulfuric acid a solvent? It is not. The acid is here to facilitate this reaction. When we looked at the SN1, we had a hydroxide leaving group. We didn't mention it then, but hydroxide is a terrible leaving group. But no worries, there are a lot of tricks we can do to make a leaving group better, to make it more apt to leave. One of those is using an acid to catalyze our reaction. So we're going to look at that here. It's going to give us an extra first step that you're going to need to be aware of. So let's write this over to the side. We're going to be investigating an acid-catalyzed reaction. This is something you'll need to take notes on. You'll need to be able to identify when that is going to occur. So if I look at this right off the bat, the first thing I still want to do is figure out, is this going to proceed according to the SN1 or the SN2? So my SN1 is going to be favored by carbocation stability. Carbocation stability comes with more substitution. Like I already said, this is tertiary substituted. I've got 1, 2, 3 carbons that this is attached to. This carbon in the middle. So this is 3 degrees of substitution. That's going to be very good at stabilizing a carbocation. So the SN1 is favorable. Is the SN2 favorable? Well, this extra methyl group down here, that is going to provide a lot of steric hindrance on the backside of that carbon, where that nucleophile is going to try to attack. So that is going to heavily disfavor the SN2. Now remember, that doesn't mean that it just doesn't happen. It means that it happens it does not happen frequently at all. It happens very rarely. So it might be 1 molecule in several billion went by the Sn2 mechanism. So we don't really need to account for it. So when we're looking at this, our nucleophile is going to be this bromine, because that's going to end up being our base, a Br-. That'll be our base. That's going to be our nucleophile. It's a very weak nucleophile, which is good for the Sn1 mechanism. But we still need to get rid of this leaving group first. That is going to be our primary hindrance. So if I were looking at this reaction without the H2SO4, it is possible that this leaving group could leave on its own. We can protonate just in water an alcohol, and it could then leave on its own. We could also deprotonate that alcohol. That is something that can also happen, and that could become an O-. But both of those things are pretty rare. So we're able to catalyze this, meaning make this reaction happen quicker by tossing a bunch of extra protons into the mix. So this often happens where we add concentrated sulfuric acid to a reaction so we can get a bunch of spare protons. So let's draw that situation out. Okay, I have drawn out all of the things that are going to be in this solution interacting with each other. It is a very busy solution. The point here, I've got them in colors, the ones that are important. The molecules that are important are in colors. The first thing that's going to happen is this has to leave. This bromine cannot do anything until there is a positive carbocation hanging out right here. So the bromine is stuck. The sodium is going to be a spectator. The water is just moving things around. It's not going to directly interact. The HSO4 minus, this is the leftover. Once the sulfuric acid loses that proton floating around in the solution. So this will end up being the leftover. I'm going to end up with a bisulfate with my sodium. Okay? So those are just spectators. They're not doing anything. But the first thing that does happen is this oxygen sees that proton, and oxygen is very good at picking up an extra proton. So it's going to have this electron pair snatch that proton. This is an acid-base reaction. It is not part of the Sn2 mechanism. This is all preparing our Sn2 mechanism. So we need to draw out that protonation of that oxygen, and that's our step. So when you're drawing this out, you do not need to draw the water, the spectator ion, or the other spectator ion. You only need to draw the things that are in color that are doing something. So we just want to draw those out just to see that. You do not need to draw them. I'm drawing them just so you can see what's going on. So the oxygen attacks that hydrogen, pulling it in, and now we get a new bond. So I'm going to draw this down, give myself some room. I'm going to start back over here. All right, now that we're all set up, we're ready to start our Sn1 reaction. I've omitted all of the spectators, so now we don't need to worry about them. You wouldn't worry about them from the start, but now we're ready to go. So, first thing to know, this oxygen, because it picked up a proton, now has that positive charge. So the oxygen is positively charged. It is a water hanging onto this carbon, so it's totally fine with leaving. It's going to take out this bond right here. That electron pair is going to go to the oxygen. And then that positive charge is going to be left on that carbocation. So now we've got this water molecule floating away. Once again, this would now be a spectator, so you would not need to draw that. I'm drawing it because this is the water that just left. So it's floating away, it's leaving. And now we've got this bromine, this bromide anion, attacking this carbocation. So this electron pair is going to be attacking right there. Now we can draw our final product. Our final product has this bromo group now attached to my methylbutane. And there we go. Now we can draw out, I'm going to erase this so we can draw out our products up here. So here's our full answer. I've got the bromo group with the NaHSO4, which is a sodium bisulfate. So now that we've got that all done, let's briefly cover that acid-catalyzed reaction. When is that going to matter? So it's going to matter when we've got an alcohol, an ester, or an amino group. Notice I've got two different amino groups drawn up here because we can have our nitrogen making further connections. But this is going to play a factor in these types of groups because these types of groups all have their own electron pairs. All of these groups are able to participate in an acid-base reaction. So whenever we have this, we're able to use an acid catalyzation in order to make a reaction more likely to occur. So all of these are normally terrible leaving groups. As NH2 as a minus, NH2, what? NH2 minus, that is a very good base. That would be a horrible leaving group. But NH3, that wants to get out of there. So NH3 is a much better leaving group, so if I can throw an extra hydrogen at this NH2, it is more likely to leave. So that's why this acid catalyzation exists. So we're going to need to keep that in mind. Anytime you see sulfuric acid as part of your solvent, you're going to have an acid catalyzation on one of these functional groups. Okay? All right, next I have a chlorobutane being reacted with sodium azonide. NH2- is called azonide. Fun fact. So, I need to figure out if this is going to be SN1 or SN2. I can look at my carbocation stability and my steric hindrance, and in both cases, I'm going to care about how substituted this carbon is. It's attached to 1 and 2 other carbons, so it is 2 degrees of substitution. Well, 2 degrees, that's not the most favorable for the SN2, but it's not unfavorable, so the SN2 will proceed at a decent pace, okay? So the SN2 will work. A secondary substitution, that does provide pretty good carbocation stability. It's not as good as tertiary, but it's still favorable, so the SN1 can also occur. So both of my mechanisms can occur here. Now, if I wanted to go further, I could look at what's my solvent type. I could look at the relative strength of this nucleophile and say one of these is going to be more greatly favored, but the reality is I might have a pretty good mixture of products. So I'm going to go through both mechanisms. We're not going to get too deep into the specifics that would lean it one way or another, but there would be some. There's a lot of ways I could push this reaction one way or the other. But we want to keep this just an easier problem. So first, let's draw out our Sn2 mechanism. The Sn2 mechanism is going to have this, what is it called? This azonide. I just learned what it's called today. Azonide group attacking this carbon from the backside. So let's go ahead and draw that. And just for the sake of argument, let's give this some stereochemistry so that we can actually differentiate our products. So here I've got my azonide all set up, prepped, ready to attack that carbon. So it's going to have one of these electron pairs swinging and attacking that carbon. At the same time, because this electron pair is pushing in, this electron pair is going to be pushing out to the chlorine. So there's my one step. So in my one step, my azonide is going to flip the stereochemistry. Remember, this chlorine was really sticking out like this, so the backside was inside the board. And so when this azonide attacks, it is going to be attached on the inside of the board. It is going to flip that stereochemistry around. So we need to keep that in mind. So there's my products from the Sn2 reaction. It is exclusively going to be in this stereochemistry. So I can write that in. I'm going to have products that look like this. And we'll say 50%. We'll say these occur at the same rate, and we're going to get 50% of this. All right? Next, we need to look at our Sn1 reaction. So let's draw a barrier here. Let's go Sn1. In this case, I'm going to have the same drawing for my setup, but I'm going to have a two-step process. So I have my negative azonide anion, and I've got my chlorine group. In the Sn1 mechanism, the first thing that's going to happen is this chlorine group is going to leave. Chlorine is not a great nucleophile, so it's totally fine with leaving. So once that leaves, I get my next step, which involves a carbocation intermediate. So now that azonide anion is going to be very attracted to that carbocation, and it's going to attack. However, because that carbocation is now spread out flat, it could attack from the front side or it could attack from the back side, and I'm going to get a mixture of stereochemistries. So I'm going to get both. Let's go up for one. So I'm going to get both stereochemistries for this reaction. So This is gonna happen in equal proportions. With the SN1 mechanism, we're always going to have 50-50. So half of my SN1 products are this stereochemistry, the other half are this, which means overall, another 25% are going to be of that stereochemistry, and the other 25% are going to be that stereochemistry. So overall, I have 3/4 of my products, 75%, are going to be with the flipped stereochemistry, and 25%, 1/4, is going to have the retained stereochemistry. And then I'm going to have my leftovers, which is just going to be the sodium and the chlorine. And there is my entire reaction. So that is a lengthier process. That involves me going through both mechanisms, identifying what products am I going to have. If I'm shown stereochemistry at first, I need to account for it later on. And I'm going to get a mixture of products. This is going to be important. Last important point here, once we introduce the elimination reactions, we're going to have 4 mechanisms to choose from. We're going to need to use that flow chart to determine if we have a mixture of different products. In reality, we're going to lean a lot heavier to the Sn2 mechanism here because this azonide is a very strong nucleophile. So it's going to be very likely to go through that Sn2. It's not really going to wait for that chlorine to leave before proceeding according to the Sn1. So when we look at these later, when we have our full mixture, we're going to be able to identify for certain what our mixture of mechanisms is going to be by factoring in all of our details, our solvent, our nucleophile strength, our base strength, so on and so forth. But for now, we're just going to be, when you're doing the Sn1 versus Sn2 mechanisms, I just want you to look at the factors of the substrate. Just, is there steric hindrance? Is there good carbocation stability? Okay? So let's look at one more that is a little more complex because the nucleophile is going to be a large molecule. For our last example here, we have a bromopentane being reacted with sodium acetate. Now, the sodium, once again, just like in every reaction we've done so far, is just going to be a spectator. It's not going to participate at all. But the acetate is a pretty large molecule. It is an organic molecule unto itself. It's specifically the anion of a carboxylic acid. So we could do this reaction with acetic acid. We could do this with acetic anhydride, which is a more complex version of acetic acid. And it would still work in a very similar way, but there would be some extra steps. So we're using the acetate anion to skip those steps. But this is a very common substitution reaction known as an esterification. It's extremely well known. It's widely used in making flavorings. And more often it uses the acetic acid version. But we're going to skip that extra complexity by just using the acetate. So the acetate anion is going to look like this. Now, acetic acid would normally have that hydrogen right there. The lack of the hydrogen causes this to be a resonance structure. So officially, it would look more like this. Technically looking like this. We're not going to get that complex. We're just going to treat this as one of them having a single bond. So there's our acetate anion, but this is going to be our nucleophile. So this is much larger than anything we've encountered before. And we can have very large nucleophiles. So this stuff can get really big. So what we're going to have here is our substrate with the bromo group is going to be attacked by this acetate. We know that this is going to be our anion, or our nucleophile, because it is an anion. We're going to have this negative charge attacking this carbon. So is this going to be the Sn1 or the Sn2? Well, Sn1 would require this to be a little more substituted than it is. This is a primary substitution, 1 degree. So this is going to proceed according to the Sn2. Very much favored Sn2, disfavored Sn1. So we only need to worry about the Sn2. So let's go ahead and draw out our mechanism. Okay, notice I've got one oxygen in red, one oxygen in black. The oxygen in red is going to be the one that's carrying that negative charge. Like I said, in reality, this would be resonating, and either of these oxygens could act as it. We're going to keep it simple. You should too when you're doing practice. So this oxygen is going to be the nucleophile attacking this carbon. So we're going to have this group attacking here, pushing away that bromine. So there we go. So in this case, I'm going to draw the intermediate step so that we can see what's really going on. So there is our intermediate step. We have both the oxygen and the bromine being attached to that carbon. Both are hanging on almost for dear life. So when this bromine lets go, we are going to be exclusively attached to that oxygen, which is going to make this an ester. So now that this reaction has gone to completion, we see that we get this product. This is 1, 2, 3, 4, 5 pentyl. And then we've got 1, 2, and this would be ethanoate. Pentyl. Pentyl ethanoate. So that's going to be an ester. This is more commonly known as banana oil, which is a flavoring in candies. It has a strong scent that is reminiscent of bananas, and it has a flavor based on bananas. So this is the type of reaction that we would use to make these synthetic flavorings, because a lot of these esters have that very specific kind of candy flavoring. If we were to use octane instead of pentane in this reaction, we would actually have produced orange flavoring. So this is a very common reaction that is done. Like I said, more commonly we would use the acetic acid, but it's a little more complex. So we can draw in our final product here. Plus, I'm going to get NaBr. I'm going to get some sodium bromide out of this. So when we go through these reactions, it's very important that we can identify what is our nucleophile, which mechanism am I going to have, and how is this attack going to look? The most important, the pickiest thing in organic chemistry is going to be drawing these arrows the right way. We want to show that these arrows are going from an electron to a destination, and we want to show them all in the right order. So be very careful drawing these arrows. That's the easiest way to lose points in organic chemistry.